So let's get started on this one. This is similar to question 8. The numbers will change, but this is a upturned cone, and the cone is 400 centimeters by 600 tall, and water is leaking out of it at this rate. And it started empty, but they're filling it up. As they're filling it up, water is leaking out. So it's a kind of combination of water going in and water going out. But the height of this water level is increasing, dH by dt, at 20 centimeters a minute. And that happened at the 200 centimeter mark. And we have to find this number C, which is the rate at which water is being pumped in. So I believe we got to that part where we wrote down what the formula for the volume of a cone is. Now what I'm going to do is use right angle triangles to find the connection between R and H. Right. So this guy up here isn't 400 anymore. This guy up here is 200 because it's only from there to there. And this guy from here to here is still 600. And that's basically that shape. And then the little baby one's this one down here. And that will be R and that will be H. So you can imagine a kind of snapshot. As the water goes up, you've got a little cone, and that little cone gets kind of taller and bigger as the water level rises. So what that tells me, because these shapes are similar, is that 600 over H is the same as 200 over R. And cross multiply, I get that relationship. Now, this fella here is kind of crucial to what I'm about to do. The rate at which the height dH by dt was told to us. So what that's going to allow me to do is to find out what R is in terms of H, and it ends up being 1/3 H. So I've got a relationship between these two guys, and this relationship is now going to be used in this formula. So that's a little bit different from what we typically do. So instead of the formula being 1/3 pi r squared h, for this particular version of a cone, the radius is always going to be 1/3 of the height. So what we've now got is 1/3 pi, 1/3 h squared h, which with a little bit of manipulation becomes 1/27 pi h cubed. And the reason I needed the formula in this version was because you told me dH by dt, so I needed this to have h's in it. And there's not a lot I can do about the volume, but I'm interested in the rate at which the volume is changing, so it's a good idea to leave that. So now that I have got, another question, now that I've got this guy set up, we can essentially almost like start this question from the start. What are we told? Well, we're told that the rate at which the height is changing with time is 20. We're told that that happens when the height is 200. And we're going to find this guy. Well, if you differentiate, you get dV by dt. If you differentiate this, well, you multiply by the power, so you get a 9th. You reduce the power by 1, and you finish with a dH by dt. Now we'll do the plug and chug. This guy is 1/9. This is pi. H is 200 squared. dA by H is this guy. And that's when I start hitting buttons on calculators. So I'll go 1/9 times pi times 200 squared times 20, and I get 279,252 to the nearest whole number. Just that guy. And you would probably think, hey, question's finished. But the one thing I forgot to take account of was that the water is leaking out at the rate of 11,500. So that number won't cut it. That number will allow this to rise if nothing was happening. But since you're leaking that amount, you need to add on another 11,500. So the answer that they're really looking for is 290,000. And I'm looking at their answer, so they have a 3 there, so I guess they rounded off a little different than I did. And that is the end of that question. Now, that's not a straightforward question by any stretch of the imagination. But the power of related rates is that it allows us to calculate rates, essentially, right? Speed at which things change, or rates at which things change. And in order to do that, sometimes things get really ugly. So I'll give that a few seconds to mull in. And the good answer is that it is the right answer because I'm looking at it on the sheet. So I know I didn't screw up. Right. There's 3 of these. This is the second one. This is like question 9. If you're into, I think chemistry, is it chemistry? Boyle's law is chemistry or Boyle's law of physics?
Chemistry.
Chemistry, okay. So pressure times volume is a constant, okay? And in this story, C is a number, not a variable. So C is like 42, you just don't know what it is, right? So treat it like a number like 42. You are told that in this story, the volume is 100 cubic centimeters and that the pressure is 100 kilopascals and that the rate at which the pressure is changing is 20 kilopascals. So we've got this contained gas and we're pressurizing it, which would be, I guess, having a piston and crushing it. And we're going to see what happens to the volume in this world. And what we're interested in is this guy. Well, I think this is the first time that we haven't needed to create the formula. It's there. P and V are treated as independent of each other, and they're both treated as functions of T. C, on the other hand, is treated as a number, right, a constant. So I'm going to differentiate the left and the right-hand side with respect to T. Well, let's do the easy one first. Isn't the derivative of a constant with respect to T 0? Actually, the derivative of a constant with respect to any variable is 0, right? So get nothing out of that. How do you think I'm going to tackle this fella? How am I going to differentiate P times V?
Using the product rule?
Yeah, first time we've ever needed to use a product rule, I believe. So I'm going to call this F. I'm going to call this J. So the product rule is F dash J plus F of G dashed. And remember, these are derivatives with respect to T, right? So if you differentiate this with respect to T, you get dP by dt, and you leave the second guy alone, you get this fella. Plus, you leave the first guy alone, you get that, and you differentiate the second guy with respect to T, you get that, and the whole thing is 0. And now we're going to do the plug and chug. I know that guy is 20. I know that this guy is 100. I know this guy is 100. And I don't know this guy, because that's the guy I'm trying to find. Now, this one's a lot cleaner than question 8. We agree this is a lot smoother. Now, where are we going? Well, I believe that's 2000. Subtract 2000 from both sides. And then divide both sides by 100. And what are the units? Centimeters and minutes. Well, let's see if that makes sense. You've got a container, probably a piston on it. And the pressure is increasing at the rate of 20 kilopascals a minute. So you can imagine how you would increase the pressure in a gas. Wouldn't you push the piston down? And if you do that, the volume is decreasing at this rate. Can you see why that makes sense that it's a negative number? Right, if you increase the pressure, right, if you push down on something, won't you shrink its volume? So it should be a negative. Its volume is reducing at the rate of 20, well, it should be cubic, shouldn't it? Cubic centimeters per minute. And from my vague knowledge of physics, that's exactly what does happen. Right, if you take a gas and you put it under pressure, doesn't the volume of the gas reduce? All we're doing here is actually putting numbers on that. So you can actually calculate it now.
Yeah, it's kind of the fact if one thing goes up, the other must go down because it's a constant.
Yeah, which is, I think that's called inverse proportion, if I recollect. Now, the last question was the one that I was having so much fun with, is this one. And it told you that there's a Ferris wheel on the ground and that the Ferris wheel is 15 meters radius. And I guess right here, there's one of those little things where the people sit in. I don't think you should stand on it, but there, that's where the person would be. And the Ferris wheel turns. And we are told a lot of things. We are told the angle at which this Ferris wheel is turning. Right, so one complete revolution takes 2 minutes. So the rate at which the angle is changing, d theta by dt, is 1 revolution divided by 2 minutes, which eventually becomes essentially the speed of angular rotation. So we were told that, but they kind of disguised it like this. We were told that the height was 24 meters. Now, when they're talking about the height, they don't mean h, they mean the height of the ground. So we were told that the snapshot, this was 24 meters. But if you think about it, it's 15 meters to there plus this guy here, which I'm calling the height. And so that was kind of disguised as well. So they tell you what you need to know, but the numbers they give you is not necessarily the ones that you really want. They told me its height off the ground was 24, but the number I really wanted to know was this distance here called h. They told me it went round once in 2 minutes, but what I really wanted to know is what did that mean in terms of angular velocity? Now, since they tell me that the height is h, I have created a little right-angled triangle. That's this one in here. And that's fixed as 15. This is 9. That is x. If you use Pythagoras, can you see that I now know this thing? But that was hidden from me. I mean, everything was hidden. Instead of saying, oh, this is the number you want, this is the other number you want, and this is the third number you want, they told me stuff that kind of made it possible to do it, but you had to work on it. And after all that information, this is what we're being asked to find. The rate at which the height is changing with time. Find dh by dt. So I draw this, I was drawing this circle and I drew this and I drew that and I drew that and I created this little fella here. And it would have been nice if they had given you this picture, but actually you had to create one. So that's not there in the homework. Now, what's the connecting formula going to be? Well, the guy that I used was this right-angled triangle. And that is h, and this is x, and this is theta, and this is 15. And I want to find a connection between the angle And why do I want that? Because I know this number. So I know I want theta. And I also want it to have h in it. Why do I want it to have h in it? Because they told me to find that. So my clues for, because there are lots of connecting formula here. Can I use Pythagoras, for instance? Can I do some other kind of combination? But the one I wanted was a connection between the angle theta and the h. So when you look at this right angle triangle, can you see SOHCAHTOA, h over 15? So I used the sine of this angle is opposite over hypotenuse. And then a little cross multiply. That guy is the connecting formula. And that guy does not have an x in it. But he doesn't need to be there. If he's not there, that's great. It's actually less things to worry about. Now you differentiate this fella. And remember, both of these are with respect to time. You get dH by dt on this one. You get 15 cosine thetas, d theta by dt. And we're pretty much ready to plug and chug. 15 is 15, that was easy. D theta by dt is pi, that was easy. So where did this cosine of theta 12/15ths, where did I come up with that guy?
From the x that you found earlier.
Yeah. And can you see that the cosine of theta is 12/15ths? Now you put that all together, and there's your answer. It's a really good question and a really hard question. And I could guarantee if I gave that to my Calc 4 students, half of them wouldn't even know where to start. So don't feel too bad if you're thinking there's a lot to that, because there is a lot to that. But hopefully that you can, when you have time, you can just think through each of the steps and say, okay, that makes sense. But what we're looking at here is like the cutting edge of why related rates are so cool. They allow us to analyze moving objects and find out how things are changing through time. And because of that dynamic, because it changes through time, it does make your life a little bit harder. And so you have to work at it sometimes. I would have said, I don't know which one's the worst. It's a toss-up between question 8 is the worst one and question 10. I don't think question 9 was that bad. I think question 9 was probably, of the 3 we did today, was probably one you could get to grips with the quickest. Well, any questions about these guys? Because we are going to be moving on to a new topic.
I have a question about number 10.
Yes.
So why did we take the second derivative of h? Why didn't the first derivative dh over dt make sense to use as an answer?
It was. I'm not sure why you thought I did the second. I just differentiated this once.
Oh, okay, I see. And then you substituted what we already knew.
Yeah.
Okay,
exactly.
that makes
I did the differentiation with a plug and chug.
Alrighty, thank you.
Okay. Any other questions? Right, we are about to start a new chapter. And the guys that we're going to be looking at, just give myself a second. Here we go. Open up another window. Oh, darn it in space. I hate it when it does that. Don't want to see the answers. Distract me. Right, anyway, we're going to do chapter 4. In particular, we're going to do chapter 4.1. And we're going to look at max and mins. And so let's get you a little background before we get into the calculus. Get you used to the terms. And let's do a nice polynomial that goes up and down lots of times. And this polynomial is going to have a start value and a finish value. Right? So instead of it being continuous forever, we're only going to look at snapshot. And that's very often what we do. So you're going to have some function between maybe x is -10, x is +10, right? A little window of the function. And we're interested in things called their absolute max, their absolute min. I call them relative max and relative min, but they call them local maximum? Let's use that term. Right. So let's find out what each one of these is. An absolute maximum and a local maximum. I'm going to call this guy A. I'm going to call this guy at the end B. The absolute maximum of a function is the largest y value that a function takes in its interval. So it's the largest y value it takes in its interval. A local maximum, on the other hand, is typically, this is not mathematics, top of a hill. Right, so in this question here, that guy there and that guy there are local maximums. I think top of a hill fits quite nicely. Do you see what I'm getting at when I talk about a top of a hill? Local max, local min. In this shape here, that point there is an absolute maximum. Would you agree that that point is higher up than any other, right? It's the biggest y value that this function takes. Now, you have a very similar thing going on at the other end. There's a thing called an absolute minimum. In this case, it might be -10. And that's the smallest y value it takes in the interval. And then you have local minimums. And bottoms of, well, I can't call them hills. How about bottoms of valleys? Right, so in this shape here, won't that guy there be a local minimum? And won't this guy here be a local minimum? And can you see that guy there is an absolute minimum? Are we clear in our brain the difference between a local minimum and an absolute minimum? And a local maximum and an absolute maximum, right? Because they're very similar names. Now, that's the basic concept. Now we're going to do the nuances. And that gets a little bit more a little bit weird. Imagine I have a function that starts here, crawls up to here, finishes here, and that guy there is at height of 10. And that's 0. Obviously, that's 0. I'll put an x coordinate 10 or something like that, right? Right. Nothing really too strange happening to this function, but this is like a starter. This function, right, that you're looking at here, right, has an absolute maximum of 10. Agreed? Does it have a local maximum? So this is the
Yes.
nuance. Can it also have a local maximum?
Yes.
Yes. Isn't that a top of a hill? So this shape the local max and the local min are the same thing, aren't they? Sometimes a function can have both titles, right? I'm Scottish and I'm a male. I'm allowed to be both, right? It can be both at the same time. This curve, this function, has an absolute minimum. Would you agree it's 0? Does this function have a local minimum? Is it got a bottom of a hill? Not really. Don't you want that kind of shape? And I don't care what this textbook says. That's correct, and I'm right. So for a local minimum, we would say DNE, right? Does not exist. I'm going to do one change. This new function with the hole in it, right? Little non-usable value. That destroys the absolute max. It also destroys the local max because you need to have the value of the function at the point you believe the absolute maximum lives. Now you might say, well, the absolute maximum is 10, right? And the argument goes, but that function is never going to be 10, is it? Isn't there a hole at the point where it gets to 10? And you can't say, well, the absolute maximum then is 9.429s, because isn't 9.59s bigger than that one? Right? There is no specific one single number that the function is equal to that would be it. So there's a little subtlety. No absolute max, no absolute, local max. On the other hand, if I put a dot here at 13, because you know some piecewise functions have dots in funny places, does this function have an absolute max? It now does. And isn't the absolute max 13? The definition is the largest y value the function takes. Can't that largest y value be a little orphan floating in the air at the height of 13 and nobody else gets that high? So do you see the absolute max is a little bit weird? If there's a hole there, you can't use it. If there's a dot on its own, you could. Suppose that was not the dot. Suppose the dot was down here. Does this function have an absolute max? It doesn't have one again. So, doesn't have one, doesn't have one, now it's got one. Local min ain't happening. That hole kills the local max, I should say, right? Having a dot above it or below it, or not having a dot at all, does not help you for the local min or max. It's got to be a nice smooth hill or a nice smooth valley. Can you imagine me turning this shape upside down and you get similar things for local max and local min and absolute min, right? You could get it in the other side. So I could do a whole lot of questions with shapes that look like that, right? So we've got the main definition of absolute and local max and min, but isn't there the little nuance now about, yeah, it is an absolute max, but only if the function exists at that point. So let me zoom over here and show you some of the visual issues. Well, not visual issues, but the visual questions that you could get. That's actually pretty cool. Because I'm a visual learner, I like seeing pictures. I like to draw pictures of things as well when I'm trying to do them. Okay, are you looking at screen 2? Are you looking at graph right now? Okay, in this particular question, you're not going to tell the y coordinates because they don't give you them. But what you are going to give me is a letter of the alphabet. So, looking at this curve, right, what would be the x coordinate of the absolute max?
S.
Agreed. What would be the coordinates of the local max?
C.
C. And I do not care if this textbook says it's A and S. I am not going to. You may have to do it to make them happy, but no. You need a hill to be a local. That's the bottom line. You just need a hill to be local, and I'm not going to change that. Right. Does this shape have an absolute minimum?
So since it has to be a hill,
Mhm.
does that make R the only local minimum?
Not quite, no. But isn't R also an absolute minimum? I'm looking at my side. Yeah, it is, isn't it? Now, what about local minimum? R is definitely a local minimum. Now, you are looking at B and not seeing a valley. I do see a valley. It's a very steep Norwegian fjord valley, but it still counts as a valley. And so there is a local at B and there is a local at R. And there's an absolute minimum also at R. Okay. They actually agree with me. Yay. I thought they might not. Oh God, we'll probably disagree with this one.
Could you scroll back to 1 for just a second?
Sure.
Thanks. I'm good.
Then let's look at hide the answer because it's distracting. Whoa, God in Himmel. Right, I'm going to make this as big as I can. I don't know if I can make it much bigger. Okay. This shape is broken apart really badly. So let's have a look at it. Absolute maximum, where would that be?
Is R an asymptote?
No, I think it's a cusp. It's like the top of a house, right? It's not a vertical asymptote where they never meet. I'm assuming that it does meet at a funny cross, right? So it's still okay. So that's why R is an absolute max then, isn't it? Is there any local maxes floating around?
No.
You can't see any. Is there a local minimum?
D.
Agreed. Is there an absolute minimum?
A.
Agreed. Oh, that's us finished with that part. Okay. So are we happy with absolute and local max and min? And just remember, holes cause troubles. Is it possible for a function to have two absolute maximums?
Nope.
Okay, let's see if I can convince you otherwise. So I went and said, is it possible to have two? And we got some head checks. How about a function that we are aware of, the sine function? And if I did it from 0 to 2 pi, would you agree that that function has one absolute maximum and it's there and its height is 1. Would you agree? It's also a local maximum. But suppose I did the same function to 4 pi. Wouldn't that guy also be an absolute maximum? So can you see it is possible to have more than one location where the absolute maximum happens? They just have to share the same height. So if you were thinking there can only be one maximum height, you're right, there can only be one maximum height, but couldn't that happen in more than one place? I think it's easy to see that there are tons and tons of local minimums, right? And they don't even need to be the same height. Can't you have a little hill and a big hill? And there still counts as local maximums in both cases. And the same is true if you go on the minimums. So now I'm going to, yeah, I've got time. Now I'm going to talk about a topic, a concept called critical. It's either critical numbers or critical values. I want to use, I mean, both terms are used, but I want to use the same one that they're using. I would use critical numbers, but they're probably going to use critical values. So I'm just going to find what they call it. So I use the same word. They call them critical numbers. But if you go looking in YouTube videos, they're often called critical values as well. So here's our definition. Critical number is a value of x. So when you do critical numbers, you always give the x coordinate of where they are, right? So a critical number is the x coordinate, the value of x of a function, where either the derivative is 0 or the derivative is undefined. The vast majority of critical numbers tend to be when the derivative is 0, but you will get some undefined as well. Critical numbers are very important places on a function. Give you an example of why critical numbers are so useful. Imagine this function. Wouldn't the derivative at this point be 0? Wouldn't the derivative at this point be 0? And wouldn't the derivative at this point be 0? And can you see then that critical numbers very often tell you where local max and local mins live? And sometimes they tell you where absolute max and absolute mins live. And the reason why we're going to use critical numbers is if you are given a function and you didn't stick it into Desmos, wouldn't it be nice if there was a way that calculus could help us to find the x coordinate of local max and mins, and then eventually we could get the y coordinates from there. Right. Now, why are undefined sometimes useful in finding local max and mins? Do you know we saw a picture today that looked a bit like that? I think you were asking, Robin, is it a vertical asymptote? And can you see mine's a little bit clearer? You see it's a corner, right? If you want to know the fancy word for that, it's called a cusp. So when a curve meets like that, what's special about its derivative? Well, its derivative is undefined. Can you understand why you couldn't get a tangent line at that corner? Because on one side, isn't it going kind of up the way, and the other side is, you can't have two numbers, right? And you can't really like balance it like a piece of wood on the top, because that's not really fair either. So it's undefined. And so we are interested in that. Of course, some critical numbers are not actually that helpful. if you do the cube root function, I don't know how well I've drawn it, but in the cube root function, at x equals 0, doesn't the curve go vertical for a little while? And you know the derivative of vertical things is undefined, right? So don't be caught up with the idea that if you know all the critical numbers, that you're guaranteed to get a local max or a local min at those places, right? That you're guaranteed to get a hill or a valley. You could just be unlucky and get an undefined one that was nothing special. Would you agree at that point in the curve, nothing particularly interesting is happening as far as max and mins are going? So we do very often have to take that into account. Are we comfortable with what is meant by critical number? It's the x coordinates of a curve where the derivative is 0 or undefined. Okay.
So did you say that the cube root of x does not have a max or a min?
Correct.
Okay.
Cube root function goes on forever. It gets big very slowly, but it gets bigger forever, and it gets negative forever as well. So it has no max or min. It has no hills or valleys, right? So it has no local max or min either. Any questions about that? Okay, let's just do one, just so that when we start tomorrow, we kind of can do this as an overlap. Suppose I have a function and it's x cubed take away 27x. Now, yeah, you should know from 141 that's a cubic. Would you agree that most cubics look like that? Now, in my very bad sketch of that cubic, would you agree that this cubic has probably got a local max and a local min? For sure, right? Let's find out how critical numbers help us. If you differentiate this guy, if you differentiate this guy, there we go. If you pull out a common factor of 3, and then you factor the heck out of it, in other words, style points. So you know all those times I've been pushing style points, you are going to be glad that you're good at making things look pretty. Because if you want to find out when a derivative is 0 or when it's undefined, don't you want it to have the style point look, that it has factored as much as you can and it looks like the original. Now in this case here, won't this be equal to 0 when x is -3 and when x is equal to 3? So if I actually drew the cube, this particular cubic function a little bit more accurately, I think you would find it looked like this. Can you see that we've identified the local max and min on the cubic function? And therefore, shouldn't I be able to find the local max and min? Wouldn't the local max be the value of the function at -3 and the local min the value of the function at +3? And when we come in tomorrow, we're going to do lots of practice at finding critical numbers. And that's all, just finding them, not doing anything with them. And then at the end of this section, we're then going to use finding critical numbers and then going to use them to find the absolute max and absolute min of a function. Right? But it will always be within an interval. You know, from x equals 7 to 10, right? Or 0 to 20 or something. Say hi and bye-bye.